Hi, and welcome to a lecture on multi-agent learning. Today we'll talk a bit about teaching strategies because I still owe you an explanation of the Bully teaching algorithm. So I only will discuss Bully because you will need this for your programming assignment, and I leave the other algorithms untouched. So I won't discuss Godfather and extensions of Bully and Godfather. So, Bully was first proposed by the researchers Michael Littman and Peter Stone as part of a more complex strategy in which Bully was just a part of. Bully fits within the so-called K-Markov joint action-based reply rules, which contrast with, for example, fictitious play that depend on the entire history, and Bully, for example, does not depend on the history at all, and differs with other reply rules, some of which you may recognize from previous lectures, like IGA and Wolf-IGA. Red Valor we didn't discuss, but No Regret Learners we certainly did. So it's the point of showing this picture is that Bully and Godfather and instances thereof are really new type of algorithms. We move on to the next slide. So Bully amounts to playing any strategy that gives you the highest payoff, assuming that your opponent is a mindless follower. So Bully works very well, for example, against fictitious play. Now, how does Bully work? Suppose you are the proponent, so suppose you are the role player, and you play against the column player. And you want to force the column player into a specific action. You have to take the following steps. First, for every action of yourself, you find the best response of your opponent. So for top, this would be the best response of your opponent would be left and middle are both equally best responses, so left and middle. And for your center action, that would be middle and right. And for the bottom action, that would be left and right. So the idea is that if you play top, then your opponent is likely to play left or middle. If you play center, then your opponent is likely to play middle or right. And if you play bottom, then your opponent is likely to play left or right. Doesn't make sense for your opponent to play middle because it gives him or her lower payoff. So that's what I just told you. So then you compute what you will receive for these opponent's actions, and you will receive 3 and 8 for left and middle. You will receive 6 and 7 for middle and right, and you will receive 3 and 7 if you play bottom throughout and your opponent is a follower. Then you will receive either 3 if your opponent chooses left, or 7 if your opponent chooses to respond with right, or a mixture thereof because your opponent is indifferent between left and right here. So, and finally you choose one and only one of the actions with the highest security value. The security value is the minimum value of the payoffs that your opponent chooses for each of your own actions. So here the security value is 3 because it is lower than 8. It is smaller than 8. Here the security value is 6 because we have to choose among 6 and 7. 6 is the minimum. And here the security value is, we have to choose between 3 and 7. 3 is the minimum, is 3. So we choose C, because then we are certain that if the opponent is a follower, he will play either middle or right, but we know we will get 6 utilities for sure. So that's the idea of bully. So bully presupposes that the opponent is a follower. If the opponent is not a follower, then this whole idea of that your opponent adapts to your choice of action does not work. Next slide. So I had an idea for an app to learn to play against bully, but I didn't have the time to work that out, so I made a mock-up and made a screenshot of this mock-up. So the idea is you play against a computer, so you are the row player and you have the availability of 3 actions, and the computer has availability of 3 actions as well. And at the outset the computer initializes to either bully with the probability of 50%, or else fictitious play also with the probability of 50%, and that choice you don't see. And after the computer has chosen, it sticks to that strategy, and then you start playing without knowing if your opponent, so the computer, has chosen for bully or fictitious play, unless you cheat. So there I made a cheat switch, and if you switch it on, you can actually see what the opponent has chosen, but in the actual version of the game you aren't allowed to cheat, of course. And then the challenge is to try to press regret down as within few rounds as possible. So the point of this exercise is that you, at the outset, you have to discover where your opponent is bully or fictitious play, and then if you think your opponent follows the bully strategy, then you have to play as a fictitious player, because that's the best play against bully. And if you discover that your opponent is a fictitious player, then you have to act as bully, because that's the best play against fictitious play. So you learn to either to play bully or to play against bully, and that's, I think, the best way to understand well, the algorithm. Next slide. So I will now attempt to give a precise definition of bully. Well, I repeat the definition of bully. It is to play any strategy, and it may be a mixed strategy, that gives you the highest payoff, assuming that your opponent is a mindless follower. Well, it turns out that the precise definition of bully is surprisingly difficult to capture in an exact definition. So luckily we have the notion of best response, and this helps us out, although this definition still is a bit tricky to read, so I will go through with you in steps, and in the next slide we will dissect this formula once more. So I hope that helps to understanding the precise definition. It's funny because giving a precise definition is quite difficult, but implementing it is more easy than giving the definition. Well, you would assume that if you want to implement it, you have to know the definition. But it turns out that understanding the examples of bully is enough to actually implement the algorithm of bully. So, the set of all strategies that comprise bully for player I, so I is the proponent, for example the row player if you have a 2x2 game. The set of strategies of bully for player I is defined as, well, of course, you maximize over all strategies that are available to you as a proponent. So this is logical. But now you have to think, what is the term you are maximizing on? So of course you want to have a strategy that maximizes utility. Well, as the example shows, you have to maximize the minimum payoffs of the strategy your opponent or opponents follow. And it is your utility. And which strategies do your opponents follow? Your opponents follow a best reply to your original strategy. So this is your original strategy. This original strategy has a set of best replies, and the strategy of the opponent must be an element of that set. And this combination gives a utility for you. You must take into account the worst case scenario, which is the minimum payoff for any one of the best replies to your original strategy. You have to maximize over this minimum. If you don't understand the notation argmax, look it up in Wikipedia, or it's a standard notation. So it says, pick out the strategy with the maximum value for this expression. So this expression you can only vary with this variable s sub I, and giving s sub I, the opponent may choose s sub minus I, or the opponents. So this is the variable, and you have to vary this variable s sub I, your own strategy, to maximize the minimum payoff. So it's quite a complicated formula actually. So the rightmost inner part is the best response of your opponent to your strategy, and the middle inner part, as from here, is the guaranteed payoff for bullying your opponent, and the entire formula maximizes this guaranteed payoff. And if you read the formula well, you recognize the max min, that is the security value in this formula. You maximize on the worst case scenario. You maximize on the worst case scenario. Next slide. So actually, if you write out the best responses in full, that's also an argmax formula. That is the set of all counter strategies to your strategy, the set of all counter strategies. So this is a set here, the left hand side is a set. So the right hand side is also a set. The set of all counter strategies that have the highest utility against your strategy. So these are just the best replies of your opponent. So this is a set that is computed by your opponent, not by you as a proponent. So if you define a bully for player I for this specific strategy s sub I, it's the guaranteed payoff for playing this strategy against mindless opponents. And then you will have this definition. So this definition hinges on the strategy s sub I and does not yet maximizes on the best strategy. So the strategy is fixed here, and then you maximize on the for each strategy you compute those strategies SI that have a maximal payoff. So in a way this looks a bit like a fixed point definition. So obviously Boolean is a stateless or memoryless learning rule. Doesn't need a course of history because it keeps playing the same action throughout, doesn't change action. So, and that's it. Because next are extensions of Boolean, but we won't discuss that because we don't need it for the programming exercise. So thanks for listening, and hope to see you next week when we have a last presentation on approaches for comparing multi-agent learning strategies. Hope to see you then. Bye.